Hello guys. So in this video, we're going to talk about stress, strain, and Young Modulus. And at the end of this video, we should be able to know the definition of stress, strain, and Young Modulus, the equations that relate stress, strain, and Young Modulus together, how to solve for stress, strain, and Young Modulus, and also simple questions, simple calculation question that involves stress, strain, and Young Modulus. So first of all, what is stress? Stress is the force applied per unit cross-sectional area of a material. It tells you how much force is acting on each square meter of the material. Stress itself is given by this symbol. The symbol is called sigma and is equal to the force divided by the area. This equation reminds us of the pressure equation. Pressure is equal to force over area, and it has an SI unit of what? Pascal. Is either we write Pascal or we say it's equal to Newton per meter squared, since force is in Newton and area is in meter squared. All right, we move on to strain. We say strain is the extension per unit original length. It tells you how much a material stretches compared to its original length, how much it stretches compared to its original length. So the strain is given by the symbol epsilon, which is equal to the change in length divided by the original length. The change in length divided by the original length. The change can be called the what? The extension. We take, for instance, when you get a spring, you apply force to stretch the spring. When you're stretching the spring, the spring increases in length. If the original length is L, the change in length is going to be the new length it increases to minus the original length. That's going to be the change in length, which is delta L. So since delta L is in meter and also L is in meter, you observe that meter cancels out. So the epsilon here, which is the strain, has no units. So this is dimensionless since it has no units. Then we'll go on to Young modulus. We see Young's modulus is the ratio of the stress to strain within the elastic limit. So if you remember Hooke's law states that the force you apply to a given elastic material is directly proportional to the extension, provided that the elastic limit is not exceeded. So provided that this elastic limit is not exceeded, that's when Young's modulus holds. So Young modulus is the ratio of the stress to the strain. We say it is the stiffness, the measure of the stiffness of a material, that is how resistant it is to being stretched. So the Young modulus E is given by the ratio of the stress to the strain. And this stress, we said it is sigma, and the strain is epsilon. Since the epsilon here is as a unit and no unit, so our Young modulus is equal to what? The SI unit from Young modulus is Pascal or Newton per meter squared. So this at the back of our mind, let's take some questions that we'll have to use these equations to solve. I will solve two questions and I'll give you one to solve. The first question here says that a steel wire has original length L equal to 2.0 meter and diameter D equal to 1.00 millimeter. A tensile force F equal to 50 Newton stretches the wire by 0.600 millimeter. Calculate the stress, the strain, the Young modulus. So first of all, let's write out our parameters. The length is equal to 2.0 meter. The diameter is equal to 1.0 millimeter. And you know diameter, if you're converting millimeter to meter, you just multiply it by 10 raised to the power minus 3. And this becomes 1.0 times 10 raised to the power minus 3 meters. All right, then we're also given the force. The force is equal to 15 Newton. So we use this to solve. Remember we said that the stress is equal to the force divided by the area. Here we know the force to be 15 Newton, but the area is unknown. But if we consider the wire, the equation we use for solving the area of the wire is equal to what? Pi r squared. So we use this equation to solve. Now we are given the diameter. We don't know what the radius is. But if you look at it, the radius is equal to diameter over 2. So we can replace this in the equation. Instead of putting radius, we just replace it with the diameter divided by 2. So our area will be equal to pi d over 2 squared, which is equal to pi d squared divided by 4. So we can use this equation to solve for the area. Area will be equal to pi into the diameter, which is 1.0 times 10 to the power of minus 3 all squared, divided by 4. So if you punch this in your calculator, we're going to have the area to be equal to 7.854 times 10 to the power of minus 7. So this is the value we use in solving for our stress. So the stress, which we said is equal to force over area. Our force was given as 50 Newton. In our area is 7.854 times 10 to the power of minus 7. So just point this value into our calculator as stress. Let me quickly do that with my calculator. Stress is 50 divided by 7.854 times 10 to the power of minus 7. It's 6.37 times 10 to the power of 7 Pascal. So we'll go on to the strain. So strain is equal to change in length divided by the length. So the change in length from the question, it is 0.600 millimeter. So this is going to be 6.0 times 10 to the power of minus 4 divided by the length, which is 2.0. And this gives us a strain of 3.0 times 10 to the power of minus 4. Remember we said the strain is unitless. So we keep on going. Now we solve for the Young modulus. The Young modulus, which has a symbol E, is equal to the stress divided by the strain. Now we solve our stress before to be 6.37 times 10 to the power of 7 divided by the strain, which is 3.0 times 10 to the power of minus 4. So quickly plunge this into our calculator. Our Young modulus E is going to be equal to 2.12 times 10 to the power of 11 Pascal. Okay, that answers this question. So the stress is force over area, which is 6.37 times 10 to the power of 7 Pascal. The strain is 3.0 times 10 to the power of minus 4. Since it is unitless, we add nothing to it. Then the Young modulus is 2.12 times 10 to the power of 11 Pascal. So move on to our next question. The next question here says that a copper wire of length 1.5 meter has a Young modulus of 1.10 times 10 to the power of 11 Pascal. If the diameter of the wire is 0.8 millimeter and carries a tension of 120 Newton. Calculate the extension of the wire. Now we write out our parameters. The length of the wire L is equal to 1.5 meter. The Young modulus E is equal to 1.10 times 10 to the power of 11 Pascal. The diameter is equal to 0.80 millimeter. As far as the tension is the same as the force. Force is equal to 120 Newton. What they ask us to find is the extension, which is change in length. We don't know. All right. So in solving this, remember we said our Young modulus E is equal to the stress, which is sigma, divided by the strain, which is epsilon. Now, they gave us the length, they gave us the Young modulus, they gave us the diameter, they gave us the force, and they also gave us the change in length, which is the extension. So from this, if we are able to solve for our strain, then we should be able to solve for our extension from the strain, because strain is equal to change in length, which is the extension, divided by the length. So if we can solve for the strain from this equation, then we should be able to solve for the change in length. So let's go on to solve for the strain. So we impute into this equation, but before we impute, let's solve for the stress. The stress is equal to the force divided by the area. But now we don't know the area. The area is equal to pi r squared, or we can say pi d squared divided by 4. So the diameter was given as 0.8 millimeter. So this becomes pi d is 0.8 times 10 to the power of minus 3. Since we're converting to meter, all squared divided by 4. So we punch this into our calculator. The area is going to be equal to 0.027 times 10 to the power of minus 7 meter squared. So we go on to solve for the stress. The stress will be equal to the force. The force was given as 120 Newton divided by the area, which is 5.027 times 10 to the power of minus 7. So we'll quickly punch this into our calculator. So this gives 2.39 times 10 to the power of 8 Pascal. Now we know our stress, so we can go on to solve for the strain. Remember, we said that the Young modulus E is equal to the stress divided by the strain. So if we make the strain the subject of the equation, we're going to have the strain to be equal to the stress divided by the Young modulus. Now the strain is equal to the stress we got as 2.39 times 10 to the power of 8 divided by the Young modulus. The Young modulus was given in the question as 1.10 times 10 to the power of 11. So we quickly punch this into our calculator. We get our strain to be equal to, that is 173, times 10 to the power of minus 3. So the strain is unitless, so we don't need to add a unit to it. Now we know the strain. We're looking for the extension. We know that the strain is equal to the change in length, which is the extension, divided by length. Now, if we make the change in length the subject of this equation, the change in length is going to be equal to the strain multiplied by the length. So the change in length is going to be the strain, which we got as this value, 2.173 times 10 to the power of minus 3, multiplied by the length, which is 1.50 from the start of the question it was given. Now the change in length is going to be equal to 0.26 times 10 to the power of minus 3 meter. So since it is change in length, it's going to be in meter. So this is the answer to the question. So we're just going to try this. The question here says that a steel wire has original length of 1.75 meter, diameter 0.90 millimeter. The tensile force of that stretches the wire by 1.03 millimeter. Calculate the stress, strain, Young modulus.